morning, class! My name is RCP Viola, but you can call me Teacher RC, one of your teachers for today's lesson. Now, before we begin to our discussion, may I request everyone to please stand up for our prayer. Please lead the prayer. And in the Father, the Son, and the Holy Spirit. Amen.
Now, let me introduce first our classroom rules during class discussion. First, quiet when there is someone is talking or answering. In short, behave all the time.
Second, listen attentively because I might call names for some question. Third, you are not allowed to go out, stand up, or roam around when the teacher is discussing. Not unless if it is emergency.
Fourth, if there are questions or clarification, just raise your hand for you to be identified immediately. Lastly, be honest during quiz time. Is it clear? Alright.
I want to remind all of you that every student who participate in the discussion will get a sticker with equivalent points. I have here a heart is equivalent to 5 points, a star is 3 points, and a smile face is 1 point. And you also have sad face is equivalent to -2. If the student is noisy during the discussion. Is it clear, class? Alright.
Now, let's go back to our last discussion if you still remember. Who can tell me what was our last topic last meeting? Yes, what is our last topic last meeting? Very good. It's all about inductive set. Now, who can tell me what inductive set all about? Yes, please.
Very good. It seems that you clearly understand the topic. Let's give her a hand. Alright. Going on, let's have a game first. A 4-pick, 1-word game, but with a twist. Before you are going to answer, you need to say first, I believe, and last word, and I thank you. Is that clear? Alright. Are you familiar with the game? Okay. Now, are you ready? I cannot hear you. Are you ready, everyone? Very good. Let's start the game. Who can guess the first picture? Who wants to answer? Yes, please. Equal is correct. Very good. Now, second picture. Who wants to answer? Yes, please.
Very good. Numerous is correct. Now let's proceed to number 3. What is your answer? Almost correct. Any answer? Yes, please. Reflexive is correct. Very good. Now let's proceed to number 4. Who wants to answer? Yes, please. State your answer. Symmetric is correct. Very good. Now, number 5. Who wants to answer? Yes, please. Bijective is correct. Very good. Last number. Anyone who wants to answer? Yes, please. Transitive is correct. Very good.
That's all, everyone. Very good. Did you enjoy our activity? Did you learn from it? Alright, very good. Let's give a hand of applause to ourselves. Okay, class. Now I have prepared an activity here. All you need to do is to find an equimorous partner of each card. I'm going to group you into 4 groups. Counting start here. And don't forget your number. Alright, so what is the last number? Number 4. Since all of you are 28 students, I'm expecting 7 members of each group. Now go to your group. Group 1 at the right side, Group 2 at the left side, and Group 3 at the back of the Group 1, and Group 4 at the back of Group 2. At the count of 10, all members should be in their groups and already form a circle. The first group who create a circle in silence will receive a plus points. Alright, the count starts in 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Alright, so group 4 is the first group who create a circle in silence, so they will receive a plus points on the activity later. As what you have seen, each cards have their partners with the same elements inside. And all you have to do is to find a pair with a total of 14 pairs. The 4 players from each group should follow the rules. First, this should be a friendly activity, but you still need to do your best because the first group who can pick the 2 cards with the same elements will receive a plus points. Second, if you find already the pairs, you need to say EQUINUMEROSITY. And if you fail to find the pairs, the next group member will proceed until the 4 pairs are found. And third, the group that found many pairs will be the winner. Now, are you all ready? So the 4 players should be here in the table, and at the count of 3, you should start picking the cards. 1, 2, 3, go! Alright, the group 1 and group 3 already have points. Next player, at the count of 3, 1, 2, 3, go! Very good, the group 3 and group 4 have points already. Next player, at the count of 3, 1, 2, 3, go! Very good, the group 3 and group 2 have points already. Good job everyone. So as I tally your scores, the group 3 is the winner and they will receive a 50 points. And the second group is the group 2, they will receive a 45 points. And the third is the group 1 and the group 4 will receive a 40 points since they are a tie. Let's give a hand for a successful activity. Now that we are done with our activity, let's try to reflect these following questions. First, do you have any idea what is our topic all about? Don't be shy, it's just your opinion. Yes, please. Okay. And based on your prior knowledge, how do you define equinumerosity? Alright. Is it hard for you to find each pairs? Okay. So for this lesson, these are the following objectives. First, define an equinumerosity. Second, use bijective to determine equinumerosity sets and solve problems involving equinumerous sets.
Good day, everyone! Our topic today is all about equinumerosity. So let's begin. Equinumerous sets is known to have a one-to-one correspondence between them and are said to have the same cardinality. The cardinality of a set X is a measure of the number of the elements of the set. The study of cardinality is often called equinumerosity, or equalness of numbers. We say that sets A and B are equinumerous if there is a one-to-one correspondence between their elements. So class, from the definition that I give, who can give me an example of equinumerous or equinumerous sets? Yes, please? Very good, thank you. Another example. Yes, please. Very good. So, let's give them a 5 claps. 1, 2, 3, 4, 5. Thank you, everyone. Now, let's continue. Here is an example of a one-to-one mapping. We have set A and set B. So, from set A, we have A, B, C, and set B, we have A, B, C. So, from A to A, B to B, C to C. Every individual A of the first set A is matched with corresponding individual B in the second set B, in such a way that all individuals have exactly one partner in the set. Is it clear, everyone? So, let's discuss it step by step. We want to discuss the size of sets. Given two sets, A and B, we want to consider the following question. First, does A and B have the same elements? Second, does A have more elements than B? So to answer that question for finite sets, this is not very complicated. We can just count the elements in the two sets and compare the resulting numbers. And if one of the sets is finite and the other is infinite, it seems conservative enough to say that infinite sets definitely has more elements than finite sets. But now consider the case of two infinite sets. Our first need is for a definition. What exactly should A has the same size as B mean when A and B are infinite? After we select a reasonable definition, we can ask, for example, whether any two infinite sets have the same size. Here is an analogy in order to find the solution in the above problem. We can first consider an analogous problem, but one of a very simple level. Look at the picture. So, observe the picture, class. Imagine that there are too many houses and too many people. The question is, are there exactly as many houses as the people? But before that, who can read this first? Yes, the one who is raising her hand.
Imagine that your mathematical education is just beginning, that you are on your way to nursery school. You are apprehensive of going to school because you have heard that they have mathematics lessons and you cannot count past there. Sure enough, on the very first day, show you in figure 1 and ask, are there exactly as many houses as people? Your heart sinks. There are too many houses and too many
Okay,
people for
thank
you
you
to
very
count.
much. So, observe this second picture. So, what can you tell about this picture? Yes, you. Thank you. So, you are comparing this picture to the first picture that I show you. Okay, thank you. So, in this picture, how to answer the question without counting? We can now say that the set of people is equinumerous to the set of houses, as we label each person to the houses. A set A is equinumerous to a set B, written A equinumerous to B, if there is a one-to-one function from A to B. What is a one-to-one function? Okay, a one-to-one function from A and to B is called a one-to-one correspondence between A and B. For example, in figure 1, the set of houses is equinumerous to the set of people, right? Yes. A one-to-one correspondence between the two sets is already exhibited in figure 2. Right, class? Yes, as we already label each person to the houses. Let's proceed to Theorem 6a. For any sets A, B, and C, we must prove that equinumerosity is transitive, symmetric, and reflexive. So, first, reflexivity. So, A is equinumerous to A. Given a set A, the identity function on A is a bijection from A to itself, showing that every set A is equinumerous to itself. So A is equinumerous to A. Example, let A, B, and C be sets. The identity map ID A is to A is a bijection of A, where the identity A of X is equal to X for all X is an element of A is a bijection. To make it clear, let's look at this. We have set A and set B. The elements in set A, we have A, B, and C. The same as the element of B, we have A, B, and C. So to make it reflexive, or to say that it is reflexive, there should be A maps to A, B maps to B, and C maps to C. It arrows to itself. So let's proceed to symmetry. If A is equinumerous to B, then B must be equinumerous to A. For every bijection between two sets, A and B, there exists an inverse function which is a bijection between A and B, implying that if a set A is equinumerous to set B, then set B is also equinumerous to set A. Written, A is equinumerous to B implies B is equinumerous to A. So, to make it clear, we have X and Y. And X, we have A and B. And Y, we have also A and B. If there is A to B, there must be B to A to make it symmetric. Okay, now let's proceed to transitivity. So, if A is equinumerous to B and B is equinumerous to C, then A must be equinumerous to C to make it transitive. Given three sets A, B, and C with two bijections, A is a bijection of B and G is to B is a bijection of C, then composition G of F of these bijections is a bijection from A to C. So if A and B are equinumerous and B and C are equinumerous, then A and C are equinumerous also. Written, A equinumerous to B, B equinumerous to C, A equinumerous to C to make it transitive. In light of the examples presented up to now, you might well ask whether any two infinite sets are equinumerous. Such is not the case. Some infinite sets are much larger than others. The importance of equinumerosity is important for comparing the sizes of sets. For example, omega is equal to the set of 1, 2, 3, and so on. So, omega times omega is equal to the set of 0 and 0, 0 and 1, 0 and 2, 0 and 3, and so on. And we have also 1 and 0, 1 and 1, 1 and 2, and so on. We have also 2 and 0, 2 and 1, 2 and 2, and so on. So look at the figure. First, observe that the numbers of our y-axis is the sum of the natural numbers. So, we have 0, 1, 3, and 6 on our y-axis. So, example, 0 plus 1 is equal to 1. 0 plus 1 plus 2 is equal to 3. We have 3. 0 plus 1 plus 2 plus 3 is equal to 6. So, we have 6 and so on. We have also Cantor's theorem. No set is equinumerous to its power set. So, to prove this, let G is to A is a bijection of a power set of A. We'll construct a subset of B and A that is not in a range of G. Specifically, let B is equal to the set of X is an element of A and X is not an element of G of X. Therefore, B is not an element of G of X, for any X is an element of A, but B can't be in a range. That's all, class. Thank you for listening. Do you have any questions or clarification about the discussion, class? So since none, Then let's proceed to our activity. Are you all excited? Are you all ready, everyone? I can't hear you. Are you all ready, everyone? So, since everyone is ready, the same group in our first activity, all you need to do is to work as a group on answering the following question. Then, after that, the group must prepare a 3 minutes yell. Do you understand, everyone? Very good. So, I am going to read the direction. Answer the following question in a one whole sheet of paper. Note the most behaved group while answering the problem or answering the activity will receive additional points. Is it clear, everyone? Very good. So, I am going to show you the rubrics for our presentation. Here is our rubric for presenting your output. Everyone, can you please read? Okay, thank you everyone. So the second rubric is for your Yale presentation. First, mastery 15%, content 15%, smile of course 10% with a total of 40%. So, you must be guided with the following rubrics.
Good morning, class. I am Rian Vera, but you can call me Teacher Willie. I will be the one to evaluate you today, class. From the discussion that we have now, what is equinumerosity? Yes, what is your answer? Can we consider a reflexive set as an equinumerosity? Yes, please. You are all provided with a test questionnaire. You only have to do is to write your answer on your paper. Now, let's start. Okay, class? Finish or not finish, pass your paper. At the count of 10, all papers must sit by in front. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Now, for your assignment, write it on a one-half crosswise to be submitted next meeting. Directions. Make a reflection about today's discussion and relate it in a real life situation. And that would be all, class. Thank you and goodbye.